So wonderful to be here again. I think it was almost 2 years, not quite to the day, since I was here last. It's sort of slightly strange, but this always feels to me like coming to the home of volcanology, which might seem a bit odd for a bunch of medics, but because it's Tempest Anderson's house and he's been such an important figure in the history of volcanology. Although sadly he never went to Santorini, so we won't have any Tempest Anderson photos. We'll meet some other characters, but not necessarily Tempest Anderson photos today. We're in a slightly dangerous situation as well, not because of the volcano, but because I've had half a glass of wine, and I was to say every sip of wine tends to extend the talk by 5 minutes. So I'm slightly worried you may be here all evening, but I'll try not to be. Do you want to check the chat? There's are you on your iPad? Sometimes that's like I can hear nothing, and it's always a bit of a shame when you get to the whole way through the talk. There's a technical issue.
Well, that's the screen. That's you being the presenter screen.
Good. Okay. A voice from afar. So what I would like to talk to you today about is Santorini. Maybe mute. And lessons for a restless Calvera. So really studying the past, present and future of volcanic activity in this really, really fascinating system. And kind of what I want to illustrate for you today is how if you go to a little fragment of land, I mean, in this case, a volcanic fragment of land, how you read it in order to put together its past activity. And then how we marry that together as volcanologists with really some much more modern and high-tech things in order to really understand the whole system.
Yeah.
Maybe could the people online mute themselves? Would that be possible? Thank you. I'm going to start off by orientating us a bit. This is the first photo I'm going to show you of Santorini. This is looking at its bay here, and I'm going to sort of orientate you a bit there. So I'm going to start off by showing you sort of how we start looking at a landscape when we're volcanologists. And then hopefully by the end of the talk, you'll understand a little bit more about how we read that landscape, how we put together the history of a place with its future as well. So a bit of background, Santorini is here in Greece. There's Crete for orientation. This is mainland Greece here. And it's part of a volcanic arc that stretches from mainland Greece all the way over to the periphery of Turkey over here. So it's a volcanic arc that's being caused by the subduction of the African plate under this rather mashed up Aegean plate here. So we have the trench there where one tectonic plate is slipping underneath the other, and these volcanoes along the Cyclades here are a reaction to that tectonic process. And Santorini is here on this, so the arc shape, this is a subduction zone. And Santorini is here, and you can see we also have this lineament running from the northeast to the southwest that also characterizes this area. So there's a sense of the scenery here. And if we zoom in, you can see this is these lines here are the faults that you have running. So Greece is a very faulted country, as well as having lots of islands and being volcanic in some places. And in fact, that's where you get all the valleys, and where there's sort of one theory about this being why we got the civilization springing up in Greece, because we have these isolated communities in these different valleys due to the tectonic faults running through it. So Santorini sits there. It's a collection of islands, and there's basically Columbus Bank, which is another volcano off to the northeast, and then the southwest you've got Christiana Islands over here. So you've got, it's part of a series of volcanoes, both in terms of the arc shape of the subduction zone, but also this northeast to southwest lineament. And as you can see, Santorini is a collection of islands here. It's not just one island, it's actually made up of 5 separate islands. And this is now a satellite image showing us that. So the main island of Thera, here we've got the airport to give you a sense of scale. It's this sort of crescent shape island here. And if you look a little bit closer, it's kind of got these scallops. It's not a straight crescent, it's got these scallops out of it. That's an important clue for later. Then we have this larger fragment here called Theracea, this very small fragment here called Asprenici, and they form a rough sort of circle around this lagoon or bay in the middle here. And then the new islands So Palea Kameni and Nea Kameni, meaning old burnt and new burnt in Greek. So it's an archipelago of islands, and it's been really wrought by volcanism. This the original bit of the island here is a block of carbonate rock here. So that's the kind of main non-volcanic part of the island there. I'm using the pointer just so that the people online can see what I'm pointing at as well. So what I wanted to start off with is a little bit of a touristic tour around Santorini, just to orientate you. It is an absolutely stunning place. It's actually the first place I went to study volcanoes in the field just before I started my PhD. I have to say it was sort of starting with rather a high point. You know, it's, you feel pretty happy about your life choices. Well, I started off life as a chemist and then switched to volcanology for my PhD, and I have to say I felt quite happy about my life choices when I rocked up for the first call of duty of my PhD was basically reviews like this. So what I've done in these different views here, I'm going to point out some of the key features, is that the coloured triangles on the map here show you where you're looking from, so you can begin to build up a picture. So here we're at the main town with this red triangle here, looking out. You can see these shades here. That's where there's some gin and tonic and other types of bars. Obviously, I would never partake of that, but you do get the best sunsets in Greece, according to the Santorini Tourist Board, and you can sit in these places and watch the sun go down over the islands. But you can see this dark outline here. You can see some big cruise ships, because many people do like to visit, and you can see these dark outlines here, which are basically the Kameni Islands. And we're going to come on to their meaning. We go up to this area up here, looking sort of more to the south here. This is the main town of Thera here. You can see these very, very steep cliffs going down and circling this body of water, this lagoon in the middle. And you might be able to pick out a kind of ochre smudge running along the top of most of these cliffs. That's the limestone massive, the original stuff I was showing you earlier. But you'll see the cliffs are interesting. They've got all these different sort of colours and stripes within them. And if we move around now, so we move around a bit further to the north. So we're now standing at the main town looking north. And you'll see this big headland here with this sort of odd outcrop on the top. It almost looks a bit like a tour on Dartmoor for those of you who like a bit of hiking in the southwest. I'm from the southwest, so very fond of there. And you can see it again if we move further out to the purple triangle here. This is this big headland here, and there are the Kameni Islands. And then if we look across to Therasia, which is this island here up in the north from Ia, which is this very picturesque town that everybody wants their Instagram taken in. You can see the Therasia is made up of these thick layers of lava coming across. So now going to the south of the island, and every little bit of the island's a little bit different, which is one of the beautiful things. So we're now looking sort of northwards like that, and you can really pick out that wonderful ochre smudge. You can see that headland, which we're going to come back to, called Scaros over there. And these beautiful kind of tones that you get. This is in the evening sunshine. This is actually the field hotel where we stayed with the fourth year undergraduates. We take an undergraduate trip to Santorini. So the funny thing is that COVID happened, we all know about that. And this field hotel was very, very rough. It was really quite rough and ready. And when COVID happened, they took the opportunity to refurbish it, and they gave us the same price. So we took these undergraduates back to the same field hotel, and it sort of turned to a 4-star resort. And they were all like, you can see they all had their own private pools. They had room service and a glass of prosecco for breakfast, which I was very disappointed about. And they spent the week padding around in their dressing gowns and slippers, and being marched around the island to look at the rocks. But so this we kind of, we didn't resent them at all. That crew needed a bit of a treat after having been locked up with COVID. But then, of course, they told all the undergraduates the next year about it, and now they live in perpetual disappointment because we can't afford to go to that hotel anymore. But it was very nice while it lasted. So you can see how gorgeous it was, and the view that we had from that hotel there. And the view was always the reason we went. And then if you look, you see the yellow triangle here looking to the south. And again, you can see these characteristic stripes, but they're different in every different bit of the island you look at. really what's interesting is these different pieces of evidence that I've been picking out for you tell us different things about the volcano's history. One of the key things I was sort of drawing your attention to was this. Now I lost the mouse. This ochre layer, as I said, sitting on the top. And actually, if we look at this, is a geological map of Santorini. So one of the things that geologists have done over many hundreds of years is to go around Santorini, mapping it both in the surface, but also going down those cliffs to try and understand the different composition. If you look at the geological map of Santorini, you'll see most of it is this Minoan tuff, this grey area here. And that's actually what underlies most of Santorini. And you can look at it a little bit more closely. Here's a characteristic three-wheel drive van on a breeze block for scale. And this is what it looks like up close and personal. And actually, that Minoan tuff has been, the different layers of Santorini have been studied for a really long time. So they started mining that top layer, that Minoan tuff, when they were building the Suez Canal. So they came and started mining it to go build the concrete piers in the Suez Canal. They started finding all these interesting artifacts like pots and other things hidden there in that rock, in that ochre layer. And these types of discoveries and then the eruptions of the Comeni Islands caught the attention of European scientists. And one of the most influential of those European scientists was this guy Ferdinand Fouquet. And he wrote this book, very influential, in 1879, basically about Santorini and its eruptions. And his focus was very much on the Comeni Islands, because as we'll come back to, that was the main centre of activity. But he was also really intrigued by the artifacts coming out of the Minoan layer. So he was very interested in the archaeology. But he also studied the cliffs that I've shown you pictures of as well. With the so this is a really key. This is the Cape Alanaki section, which I'm going to come back to, which he sketched, and actually it was one of the first cliff sections I sketched when I went to Santorini for the first time. So Santorini's been of interest to volcanologists for a very long time, and as I said, when people started excavating that Minoan tuff for building materials, they started finding these incredible things. So the first things they found were actually on Theresea, that little fragment of that's like the second biggest island over the side. But then they found this incredible site, and I should have pointed that out on the map, the Akrotiri site, which is down here in the south of the island. And they dug it out, and it's a whole preserved settlement, and they found these incredible frescoes. So this was the Minoan civilization that was already alluded to, that centered out of Crete. So it's famous for the Minotaur, it's famous for King Minos, and they had a very important settlement on Santorini. And these incredible frescoes, a bit like Pompeii, were preserved due to the volcanic eruption. You can actually visit it. They've done a very nice job now with some EU money, I think, doing a roof over it. And you can see it was a pretty advanced civilization. They were the first civilization to have multi-story buildings. They're apparently the first civilization to have an upstairs toilet. You can see the first upstairs toilet if you go to Greece. I suggest it to Akrotiri. I suggest you go for other reasons too, but it is pretty cool. In these incredible kind of boxing. We're not sure if these are boys or girls, but they're boxing. These are animals that were the gazelles that were painted. And then I think this is one of my favourite ones because it also just shows the sort of sophistication and grandeur of their ocean-going system. And this is one of the very few precious artefacts that's been found in Akrotiri. So Akrotiri was essentially destroyed by the Minoan eruption of Santorini. But contrary to Pompeii, we've never found any bodies or people have never found any bodies when they've excavated Akrotiri. And the fact that we found very, very few of these of precious things like this is a gold onyx, but very, very few of those things meant that people clearly had enough time to get out and get safe and actually to gather up their precious belongings and move out. So for us volcanologists, even as archaeology, there's some very, very important information in terms of understanding that there were precursors. And one of the precursors is probably a big earthquake. We see like split steps if you go and look at the site. But again, when we look at the deposits, we see this evidence of early stages of the eruption that's quite different to the eruption at Pompeii. So for us, the archaeological insight is very intriguing as well as everything else. And I think you said that there's a speculation that this ended the Minoan civilization. It's quite speculative. There's a lot of mystique that hangs around the Minoan eruption. So it's been linked with Plato's legend of Atlantis because of the scale of it. But actually, I think that was an allegory rather than a real thing. It's been linked with the plagues, the Genesis, getting them out. But again, there's no real solid evidence for any of these things. But it's all rather fun and intriguing to think that that might be. And the Minoan civilization might well have been impacted by this, but there were also a bunch of other sort of power shifts that were going on in the region, so it's quite hard to tangle out the cause and the effect. So going back to those cliffs, this is actually the Alanaki section that Foucault sketched all those years. But what I want to do now is just to sort of teach you how to read into these cliffs what we're seeing. You can see here, so we're looking from the south of the island up to the north. This is Thera town up in the belly of the island there. So that gives you a sort of sense of the scale of the cliffs. And this is the Minoan deposit up at the top here. And if we go in closer and look at the Minoan deposit, and you can look at it in Akrotiri, actually there's some very nice sections, and these are some of our students studying the Minoan deposit. What the really fascinating thing is we can actually decipher the stages of the eruption. So it probably lasted about a week. We can see that the first stage, just at the bottom here, where there was some explosive activity that kicked it all off. And that's probably warned the people of Akrotiri to get out of there, to get a move on. Those were the warning signs that they didn't get from Vesuvius in AD 79. That gave them that real impetus to get themselves out and safe. Then we can see this layer here and zoom in. And what you can notice about there is it's blocky, and if you grab at it, it's really friable. It can come away in your hands, and it's just lots of blocks of pumice of relatively similar sizes. But what that is a Plinian eruption column shot up into the atmosphere and then rained down pumice from the central volcano and sorted it by size a bit. And also we know it was cold when it was in place, or cool when it was in place, because it's not stuck together. It's all separate chunks. And you can see the way it mantles the old topography, which gives us all these clues. But then if we look above, so that's the Plinian full deposit there. These are some of our students, the ones we managed to get them out of their dressing gowns at that particular point. Rather disgruntled. No, they love it. They love it. But this is the Plinian deposit here, and then above that we start to see different types of volcanic deposits, and that when we start to get pyroclastic flows and pyroclastic surges. So what actually happened was the center of the volcano blew itself out, and the waters of the bay actually flooded into the volcanic vent and started blasting material off to the sides and then collapsing the column down. And this is an enormous pyroclastic flow deposit on the top here. You can see the way it's characteristically been sculpted out by the wind in terms of the weathering, and it's that engulfs most of the Akrotiri site. And pyroclastic flow deposits and surge deposits also in Naples area in AD 79 were responsible for wiping out Herculaneum and Pompeii. So very, very hazardous type of volcanism. So that's the Minoan eruption up there on the top of the cliff. But what this view really brings out well is that's by no means the only big eruption in Santorini's history. So it gets a lot of press, there's lots of discussion about all the important things. But if we look down the cliff section here, it's pretty easy to pick out that there's another deposit here of similar size and colour to the Minoan eruption. And then there's a bunch of other stuff going on down the sides of the cliffs. Now, apart from being in a sort of a very historic part of the world, the fact that we have these cliffs cutting through the volcanic stratigraphy at Santorini means that over the modern decades, volcanologists, many PhD students, have tramped around this island. It sounds a bit disparaging. Have walked with purpose around this island and have mapped out these cliff sections and all the different parts, and have mapped out the aerial extent as well. What that has allowed us to do is actually to put together all these different types of eruption and to tie them together in different parts of the island. And one of the crazy things about Santorini is we never see its full stratigraphy in one location. So what you have to do is a bit like detective work. You go and look at this cliff, and then you go compare it with the cliff in the north or the cliff in the south. We do it with the students. But by doing all those different things, you can actually put an eruption stratigraphy together. And one of the really fascinating things is we see that at Santorini, history really does repeat itself. So what we have at Santorini are 2 cycles of explosive activity. So explosive activity started right deep down in the stratigraphy here. So you can actually see Cape Therma down here, which was down in this section here. Then it rose up through, and you can see most of the lower stratigraphy here. And this eruptive cycle culminated in the enormously explosive, or 2 enormously explosive eruptions. And Lower Pumice 2, which is not a very trendy and exciting name, Lower Pumice 2 is about the same sort of scale and composition as the Minoan eruption. And something about Lower Pumice 2, which is up here, reset the system. And then it started again with these slightly less explosive eruptions, which are missing from the stratigraphy here. But then it went through this eruptive cycle and again culminated in the Minoan eruption about 3.6 thousand years ago. So we have these series of increasingly explosive eruptions, then something enormous one goes off and resets the system, and then it builds itself up again over many thousands, hundreds of thousands of years. And what's happening at the same time as those enormous explosive eruptions is emptying out the magma chamber and sinking calderas. So that bay I showed you with those scallop shapes in the different parts, that's a series of what we call nested calderas. So we can't really date all of them, but the ones we can date, the oldest caldera 1 was about 180,000 years ago. That followed the Lower Pumice 2 eruption, and we can see fragments of that in the walls still, when we go and date the rocks using various clever techniques. So about 180,000 years ago, this is what the islands probably would have looked like, just winding the clock back. Then we can see evidence of a second caldera after Upper Scoria 1, a third caldera after Cape Riva, which was the penultimate really big explosion. And then the Minoan deposit, the Minoan eruption, hollowed out another caldera. So what would have happened when the Minoan eruption occurred is, in the middle of the eruption, the land would have actually sunk down like a piston, and crazy as it seems, it probably would have been dry to begin with. This enormous chasm would have opened up, and it was only later that it flooded, and probably not a lot later, but it actually flooded with the sea. I'm not going to talk so much about that today, but it's actually, we see evidence for it. I'll point it out later through this strait here. So you have enormous destructive eruptions, sinking calderas and shaping that bay in the middle of the island. But in between these massive phases of destruction, we also have building phases. So the island destroys itself, then it builds itself up, and then it destroys itself again. Sounds like some undergraduates, I know. But you can see evidence of this in this section here. Not the medics, obviously, are very, very sensible. A friend of mine recently went on a hen do with a bunch of medics, and she was completely shocked. Sachets of gin, apparently. And you can see these lavas building up between here, and that's part of sort of evidence for the lavas, the rebuilding of the islands. You can see these lava building, these dome forming phases in between. And if you remember the Scarra Shield that I pointed out, this enormous headland, that's what that is, the remnants of an enormous edifice that was built up between the Upper Scoria 1 and Upper Scoria 2 eruptions. So the Upper Scoria 1 eruption would have blown everything apart, and then over time the edifice built itself back up again until something reset again, probably the mass of the rock actually sitting on the crust, and allowed a larger magma chamber to build itself up again, and then you get another explosion. So this is a remnant of that, and those lavas stretched all the way around like this, and you can see them on the other side of the caldera on Terracea there. And then the most recent one here is what made up a lot more of Terracea as well, is this Terracea dome complex. So everywhere we look around the islands, what we're seeing is these cycles of destruction and rebuilding on different scales, but also this hollowing out of the earth that gives you the calderas as well. That's really what shaped the islands that we see today. So you can see here really as the volcano, the volcano has built itself up and then destroyed itself and made these enormous craters, these enormous calderas. And we see two types of cyclical behaviour. So we see these explosions that basically, these explosive cycles that build up to ever greater explosions over about 180,000 years. And then in each explosive cycle, we basically have shield building. So it builds up a new edifice and then it blows itself apart again. So those cliffs that we're looking at really tell those stories of these different timescales of cyclicity that we see in the system. And in Santorini, we're able to see that in a way that we can't in all systems because of those slices through the cliffs and because of the history and the amount of person power that's basically been put at studying this system as well. And we don't have to go back into deep history to see the rebuilding phase. So we're currently in a rebuilding phase of Santorini. So the Kameni Islands, those are dark blobs in the middle here that I pointed out to you earlier on. This is the most recent part of its rebuilding phase. So they're made up of these flowy, bubbly, rubbly lavas, and you can kind of see them coming out here. There are many, many scientific questions to try and understand about them. So the first time I went to Santorini just before I started my PhD, we actually went on a package holiday, 6 of us, to study the volcano because it was a way of keeping it quite cheap. So we turned up at the hotel welcome drinks on the first night, and we had one of those holiday reps who was trying to sort of sell us various tours. And so she looked at us, I could tell she couldn't quite work out who we were, because we didn't really fit with the sort of template of the other groups who were there, who were sort of, hen weekends and things like that. And she looked at us and said, well, what do you feel like doing? How about a rum tour of the caldera on a pirate ship? And we said, well, we'd like to go on a boat, but is it possible that you could take us on a boat and drop us off on the Kameni Islands first thing in the morning, and then we could be on the last boat that came home in the evening? She just went, what would you want to do out for? It's just a pile of rocks. We were like, exactly. That's all we want. So actually that first trip, we spent quite a lot of time, one of my colleagues' PhD projects was on it. But the typical eruption styles are blocky lava flows, explosions and domes. The last eruption was in 1950, so we haven't seen an eruption in my lifetime. We have this long history here. So we know from the Roman historian Strabo that they first emerged from the sea about 2.2 thousand years ago. So the Manila eruption was 3.6 thousand years ago. So we have a sort of sense of their emergence. But we don't know quite because that's when the submarine activity starts, and we'll come back to that. But we have 300 years of observations here, and we know there have been 6 eruptions reported since 1707. And as I say, there's lots of lovely rocky lava on these. We also have all these amazing drawings from past historical eruptions. So this drawing here is I think this is a Fava Gori drawing. Many of them are from the monasteries in the surrounds who kept these. This is some of the early eruptions of near Kameni here. So we've got Mikra Kameni in there, and then this is our friend Ferdinand Foucault, who did this beautiful sketch of what the Kameni Islands looked like in 1870s after those eruptions there. And they really are stunning drawings, and you can kind of relate. So that's Mikra Kameni here, and that's the 1707. Hello. You can see that's the fumes are making him cough. You can see the Kameni Islands there. And these days we also have a wealth of aerial photos. So reconnaissance was done in the 1940s for perhaps obvious reasons. And this aerial photography has really allowed us to put together this beautiful sort of geological maps of all the historical flows in the Kameni Islands. And it's quite tricky to do these sorts of things, to actually, to trace out these flows. I mean, if you're following the eruptions in Iceland at the moment, I think there's some really interesting lessons there as we watch the jigsaw puzzle build up of Icelandic activity about the challenges of building these flows together. So we have 70 years of aerial imagery, but actually we've gone one better than that in recent times. we've actually flown something called a LiDAR over the Khmeini Islands twice, in 2004 and 2012. This was a UK project in collaboration with the Greeks. And this is a laser beam that you sort of raster, you do a grid over the Khmeini Islands. And looking at the returns of the laser beam, you're able to get really, really good digital elevation model of the topography of the Khmeini Islands. And the fun thing is that we can tie this together with bathymetry. So people have been making bathymetric measurements again at Santorini for many hundreds of years, initially using lead plumb lines to go around and get spot measurements. And actually, this is a sort of, so people have been, this is an old map of the Khmeinis. This is I don't know if any of you had to make contour maps at school as part of geography, but I've kind of really enjoyed my papier-mâché for that. But what someone's done here is actually make layers with a beautiful wooden model of the bathymetry, and then take a photo of it for a scientific paper. So we really cheat these days. They really had to lean in to do this. We just plug a few numbers into a computer. But you can see people have studied the Khmeini Islands bathymetry there. But more recently, a Greek-led expedition has used sonar to basically map the seafloor of the caldera in much, much greater detail. And what we did with our Greek colleagues was then to stitch together our digital elevation model and that bathymetry to really make a digital representation of the whole caldera, but really to kind of look at the Khmeini Islands and try to understand what the deep topography of the Khmeini Islands looks like, as well as the shallow. And I promised I was going to I'm going to point out the scallop structure. This is the stitched together model that we have of the whole caldera. This scallop structure, I was talking about the sinking of the Minoan caldera, which is this caldera here. What the scallop structure tells us is this was dammed to begin with. This was blocked up, this sank down and was dry, and then we had an inundation, a flood, a waterfall that poured through the strait here and left this scallop structure behind, which is actually very similar to dam failures these days if you go and look at the topography. So it's quite astonishing to imagine that, really. So we can stitch these together and really try and understand more about the Khmeini Islands. And there's some really interesting things, because we had things from the historical record that didn't really make sense in terms of the sub-aerial topography. So, for example, Mikra Khmeini here, the eruptions were supposed to go on for several years, but you can see it's a very, very small surface feature. But if we start looking at the full picture, this is now the submarine. You can see these smooth areas where we couldn't get the boat in, or the Greeks couldn't get the boat in to do the sonar. And you can see a bit of loss of resolution around the coastline. But you're able to see things that you couldn't otherwise see. And so one of the things there is you can really see that Mikra Khmeini eruption there that looks so tiny on the land is huge when you see the extent of it under the sea. So we're able to see land, and that's really from Foucault's comments about that 1570 eruption, which has always been sort of something that has not made full sense in terms of the map of the Khmeini Islands. And we can watch how we can build the structure up. We can take the structure apart digitally and build it up. And I won't sort of dwell too much, but it's actually lovely. You can kind of build up these patches and see how the islands, that's the present day waterline. You can see how they're built up there. You can really wind the history backwards and forwards and look at the way that the islands are put together. But we can do something a little bit more quantitative that, and something that's a little bit more important in terms of the future hazard of the islands. So what we can do is we can use the computer model to take the lava flows off and extrapolate a surface underneath them, and then give you a volume of the lava flow. So you can take it apart in volume space as well as just in a sort of aesthetic manner. And what this allows us to do then is to think about things like how big eruptions are after there's been a repose time. So if the volcano is quiet for a certain period of time, how big is the next eruption that we ought to expect? And we can put rough plots together. So this is just a plot from the historical data that we were able to do even before the digital elevation model, looking at the pre-eruptive interval, so that's how long the volcano's been quiet for, and then the eruption length in days here. And you see that, roughly speaking, apart from the rather strange 1950 eruption, there's quite a nice, it's obviously limited data, but there's a trend that the longer the volcano is quiet for, the longer the eruption lasts for. And there's some big error bars here for various reasons associated with that technique I was talking about how you decide on your previous surface and things like that, and how you identify the runs. But again, roughly speaking, from the digital elevation model, we have a relationship with the pre-eruptive intervals, so how long it's been quiet for, and the volume of the eruption that we get. What's good and what's useful about this is it allows us to make some sort of informed forecast. Now, volcanoes always reserve the right to take us by surprise, but we can say that if a eruption happened in the next few years, so let's call it about 75 years since the last eruption in 1950, it would last 2 to 3 years, and it would erupt a lava volume of about 0.08 cubic kilometers. So that's quite helpful in terms of talking to the local hazard planners if something starts to kick off. The other thing we can do actually is compare it with historical records. So we can do this, we can sort of look at the whole volume of the Comeni Islands, we can think about typical eruption rates, and then we can work out how long it would take to build that edifice. And we can use that to say that the activity under the water of the Comeni Islands probably started about 400 years after the Minoan eruption, which has been a kind of unknown mystery, just based on how long it would take to build an edifice of that size. But actually, you could also model them as a cone and work out whether it's plausible that Strabo did see the first emergence of the islands in 2.2 thousand years ago. And it miraculously, if you take a cone that's roughly that diameter and the depth of the bay, it does roughly match up. So it's quite nice, this kind of very high-tech models that we have in terms of digitally taking the islands apart is matching up in some way, or is consistent with the deep historical record back into antiquity, which is something I sort of take some pleasure from. Maybe that's just me. But this all became a bit more important a few years back in 2011, when we started to see our friend the restless giant beginning to wake up. Now, I should say this is my former PhD student. This is Michelle Parks, very good student. And Michelle had this habit. I had 2 students at that time working in similar things. I had Susie and Michelle. Anything that Susie went to work on would immediately stop being active. So, I set her to work on the whole of Central America, and she didn't see any signals at all. Meanwhile, Michelle, I said, she went to work on look at Galeras volcano in Colombia. That erupted. Fortunately, a small eruption. So we're like, oh, okay, great, got a paper out on that. Why don't you go look at this really dusty old archival data on the Comeni Islands? So we set Michelle to look at, there was a very small subsidence signal, which was probably due to cooling lava flows on the Comeni Islands just here. So that was about, and here's our timeline, 2007. It was about here that Michelle started working on the Comeni Islands in Santorini. And what you'll see is that the Michelle effect took hold, and the whole thing started swelling up and threatening to erupt. Can anyone guess where Michelle works these days? Iceland. You got it. She actually does. If you look up, she does the satellite interferometry for Iceland. So they really have only that. She's very, very good. No, I'm joking. But yeah, so she's having actually a very stressful time at the moment, running all the deformation models for the different eruptions coming through. She's very, very skilled. This is where she learned the trade. But yeah, so Michelle started working on Santorini around here. And as I say, you see everything's quite flat and boring and calm. And then these are GPS traces. So these are the GPS network. These are very precise GPS measurements. So you can tell where they are. Everything started to basically expand like that. So they were moving apart and then moving radially as well. And you can see so if we look at NOMI is this triangle here. And you see this is the radial component of the movement. So that's going like that. And then this is the Z component, which is a bit noisier, but that's going straight up. The earthquake activity also changed. So again, this is the time since 2011, so it's starting here. And what we started seeing was that's the NOMI trace of that GPS receiver. We started seeing this cumulative count of earthquakes, these blue events here. And whereas earthquake activity had mainly been focused outside the caldera Columbus Bank previously, 2011 it moved inside the caldera here and started really picking up there. So Michelle, we changed her project a bit. As I said, she'd been looking at the small substance signal. Now, the technique that Michelle was using wasn't GPS receivers around. It was a technique called INSAR, which is a really clever technique that we have at our disposal now as volcanologists. So INSAR is a satellite technique, and it uses radar waves to basically look at the ground change, the change in the ground position. And the way it does this is by firing a radar beam down. This is one of my favorite volcanoes, Villarrica in Chile. And you can see it's done a certain number of cycles. Now, if the volcano erupts, this is actually a real eruption of Villarrica, it might empty its magma chamber out. Obviously, it's a bit exaggerated, and magma chambers aren't exactly that shape. But you might see that Villarrica's sunk down quite a lot into the ground because it's emptied out that magma chamber. And if we now send the satellite comes back every few days, and if it comes back again, it's got those extra wave bits of the wavelength there. So when it comes back to the satellite, it's actually out. It's not in phase anymore. It's got offset in terms of the radar waves. So by comparing this with this, we can basically make maps of deformation about how the land is changing. So that is what Michelle was doing over this period of unrest. And what you get these rather nice rainbow maps like this. You can't get it to work over the sea for, I guess, obvious reasons, because the sea adjusts, so you don't get that signal. But what you can see is the nice thing about it is you don't just get point sources, you get a kind of map of deformation. So you can see that the displacement was going up here. You can see this. We can model it, and basically it was like a giant was sort of blowing up a balloon centered in this northern part of the caldera there. You could do things like misfits to check how well your model's doing. You could use different satellite sensors. So this is TerraSAR-X, this is Envisat. And so by doing these cunning things in terms of retrieving that map of deformation and then modeling the deformation, Michelle was able to make an estimate of both the depth of that deformation, but also the volume of it. And so she actually came up with to get this signal, we needed a volume of about 0.01 to 0.02 cubic kilometers at about 4 kilometers depth. So what was interesting for us is that's about a quarter of the predicted flux, or the predicted volume of the next eruption of the Khomeinis. So if this was all magma, and that's a good question about whether it was, this was an enormous flux of magma coming into the shallow system in one relatively quick go. And what we did was then to compare it with other measurements from previous eruptions of the Khomeini Islands made looking at the rock record, and also previous eruption evidence from the rock record of the Manern eruption. And pulling all this together, this seems to be something quite characteristic of the system. We do not get a constant drip. We get these big pulses of magma rising up into the shallow system. And we looked for other evidence of that as well. So Michelle went back onto the Khomeini Islands with some gas measuring equipment. So she was looking for carbon dioxide seeping out of the ground. It's not the sort of gas that you see firefighting around in Hawaii. It's coming out quite stealthily. But she did a series of gas measurements and actually made some very interesting observations about the fact that CO2 gas really fluxes through the system when you get earthquake swarms. They seem to open it up. And we saw these variations. And she pulled all these different measurements together. And this was sort of the final graph really, was to see that you could see these two pulses of, so this is the deformation trace, and then this is the seismic release. So you saw these two pulses of magma actually coming from deep into the shallow system. So it's quite incredible really that we are able to see these changes. And what we could also do then is take these lessons for a place like Santorini and think about how they compare to other caldera systems around the world. So another caldera system that you might have heard of, or you may not have done, is actually the Campi Flegrei, which is in the Bay of Naples. So many people think of the Bay of Naples as being dominated by Vesuvius, and Vesuvius is a very important volcano. But actually there's a far larger volcanic system just off to the west of Vesuvius called the Campi Flegrei, and that's an enormous caldera forming system. And a bit similar to the the Santorini. At the moment, it's in a much smaller phase of activity. So the last eruption was Monte Nuovo, which is just this little cone up here. So probably what will happen at Campi Flegrei will be another little outburst of a little cone. But building up these, because these caldera forming systems are so dangerous, but so infrequently active, actually building up this database that we have of these different types of volcano and the data that we can get and comparing the different systems is really, really important. So I have a few sort of final thoughts, which I hope what I've really talked, sort of given you some insight into, is how we go to a little piece of landscape and take it apart. And we take it apart both with a pencil and a pen in terms of sketching it and making measurements and going around and looking and taking rock chunks back. But we can also use high-tech techniques now, and those are really, really complementary. And bringing all these things together actually allows us to have a much greater understanding of these really, really important laboratory systems, which then we can take those lessons and try and understand from different places around the world. So I was just going to do a plug to my publisher to say I have to do this, which is very embarrassing. But I've got a book coming out, and I was going to ask if you would allow me to do the first ever reading from the book in Tempest Anderson's house, just to finish off about the Comeni Islands. So this is one of Tempest Anderson's photos, which is in chapter 2 of the book. So this is from Santa Maria in Guatemala, and actually I've just been looking at one of the other photos there. So he figures in chapter 2 about his there you go, a British eye surgeon and keen amateur photographer and volcanologist from York. So he's there in the book, and then this is the chapter on Santorini. So if you won't mind, I'll just finish up. I did my first ever book reading. I haven't even got the final copy, but so I'm just going to talk to you about this is a bit about how I felt when I was working on the 2011 unrest in Santorini. And when it came, when it fortunately, anyway, I'll just read. Although the 2011 unrest fortunately came to nothing, it reminds us that the volcano is far from dead, and it's a matter of when, not if, it will erupt in the future. Having spent considerable time imagining Santorini's past, this activity gave me a chance to imagine its future. The course of the next eruption, which based on past behaviour you might expect sometime in the next century, will probably follow the historical accounts of those from near Comeni. It will likely start with visible swelling of the Comeni Islands and noticeable shaking of the islands in general. The waters of the lagoon might bubble or boil and turn white, orange or red as they are heated by the fresh magma. Those nearby may notice the pungent rotten egg stench of hydrogen sulfide gas. After days, weeks, or maybe months of these overtures, the eruption itself would begin in earnest with a vent opening, likely somewhere on or near Comeni. A lava dome will start to inflate and push out of this new conduit, perhaps yielding blocky lava flows and adding new layers to the island's architecture. This extrusion of lava will be punctuated by small explosions, sending occasional small dusty clouds shaped like cauliflowers or twisted rope hundreds of meters into the atmosphere, likely similar to those I saw at Santiaguito. From a distance, the hot rocks around the vent will glow like embers and will be especially impressive at night. Up close, the sound of the volcano growing will be complex at times, very loud, and at other times subtle and perhaps eerie. Thank you very much. I didn't do too badly.
Very well. You have a glass of wine.
Yeah.
Tamsin has agreed to answer any questions, if there are any. I just want to say, so are these Comeni Islands, are they actually rising as well?
No, so they stopped rising. They did. They rose, and then in 2012, fortunately, they flattened off.
Right. So when I was sitting with my feet up in one of those hotels with my Chiang Mai cocktail, I can't remember seeing those islands in the water.
Oh, right.
I must have. I'll have to.
It was a good cocktail. I'll have what she's having.
I'll have to go back and look at the pictures.
You had to go, yeah, you had to go back again.
Yeah. There's also a lovely beach with our pyroclastic cliffs
Yes.
on the other side of the
Yes,
isn't
that's
there?
right.
Yeah, lovely. Are there any questions? Yes.
I thought that was brilliant, really gripping. Looking forward to the film script from you.
Yeah.
I wanted to ask you about energy, please, and that is that so many of these measurements depend on distance and time. But what are the sizes of the energy involved in eruptions, and can one gain further insight from looking at it from an energetic perspective?
Yes. The question is on the energy.
Do you want me to repeat it?
Yes, please.
So it's about what insights we get from eruptions in terms of thinking about them from an energy perspective.
Yeah.
Is that a good? Yeah, it's really fascinating actually. I mean, so I was talking about the Plinian eruption column that we would have got at the beginning of the Minoan eruption, and then the rainfall of pumice. One of the interesting things when you think about it from energy from that, so actually for a long time people thought it was all about kinetic energy. But then when you started doing the calculations, you realised that if you just fired those bits of pumice out with the speeds that you measure coming out of volcanic vents, and actually it's limited by the speed of sound and air because of the way the shockwave propagates, they wouldn't get high enough in the atmosphere to get the fine or the finer pumice as far away. Right. So one of the really interesting things, taking it apart from an energy perspective, is that the driving force of even what looks like it's incredibly a kind of a ballistic eruption is actually the heat energy of the volcano. So what the volcano does to achieve that enormous Plinian eruption column is, I mean, it doesn't seek to achieve it, it just does it, anthropomorphize it. The hot rock is coming out, and then the background atmosphere gets mixed in with the hot rock, and the hot rock heats up that background atmosphere, and it's convection that drives it really fast. So yes, we're always trying to, I tell my students this, it's all about the physics, it's all about the chemistry. Volcanoes are energy converters, but they don't, you've just got to remember all your different sources of energy that you have there.
And does it make a difference to have the sea as a cooling effect?
Yeah, so that, I mean, that's, so if you have a little bit of seawater getting in, it can actually make the plume more buoyant because it reduces the density, because it flash boils and you've got that gas, and that actually can add to the ballistic power as well. But then as more and more gets in, exactly, you could end up quenching because of the latent heat in the water, and that's why you get that's one of the reasons why you might get pyroclastic flows coming down, because it stops having enough energy to get into the convective phase.
Thank you.
Thank you.
Thank you very much. The 19th century saw two massive volcanic events, one which ruined Mary Shelley's Summer by Lake
Summer
Geneva.
Holiday, yeah,
and the other Krakatoa later. Those completely changed the climate in Europe for a year or two. Now, I'm a bit worried by your figures on the length of time since the eruption, leading to the power of the eruption when it happens. Why haven't we had any eruptions like that in the 20th century?
We have.
Get some in the 20th
1991, the Pinatubo eruption in the Philippines cooled global temperatures by a couple of degrees. But yeah, I mean, Tambora is the year without a summer, so that's 1815. That's where the Mary Shelley's rather cruddy holiday in Geneva, by Lake Geneva, came from, and Frankenstein, Lord Byron's poem Darkness. But that was, so Tambora was it was a very big eruption. We haven't had that large an eruption in recent times. We will again. We just don't yet know when. But Pinatubo did cool global temperatures by several degrees for several years. and Tambora was just a little bit bigger, so it was a bit more of an effect. It also is not like, it's not just a simple kind of size equals temperature perturbation thing, because it depends a little bit on how it interacts with the different oscillations in the atmosphere and what time of year it goes off. If it goes up in the the tropical eruptions tend to have bigger effects than the high latitude eruptions. So Hunga Tonga, which went off just over a year ago, is really fascinating because that got a whole load of water vapor up into the stratosphere. So we're still sort of unpicking what the consequences of that have been. But that's a different type of eruption again, so we've still got a lot to learn.
What about Krakatoa?
Well, Krakatoa had smaller, I mean, it's a yeah. I talk about it, this is in the book again, this is chapter 4, but it's gonna keep plugging it. No, so it's really fascinating because they didn't actually identify Tambora as the source of the year without a summer. So they have these kind of reports on newspapers of these terrible weather and all the rest of it on one part of the newspaper page, and then they have this report of a raft of pumice on the other part, and they never join those dots up. But then with Krakatoa, we had the lying of the undersea telegraph cables. This was 1883 now. So Krakatoa, the news spread like in hours about this enormous eruption, and it was sort of different times. So the barometers in various gentlemen's clubs, largely around the British Empire, it has to be said, the people were like kind of going and looking for the traces of Krakatoa. So they saw these pressure waves from Krakatoa go around the planet 7 times. And people noticed all these amazing sunsets, so Krakatoa sunsets, but the temperature change was much more muted because it was a smaller eruption. So if Tambora and Krakatoa had been reversed, I think we'd have understood much sooner the potential of volcanoes to cool and change the environment than we did, because it was just that people didn't join up cause and effect with Tambora, but they did with Krakatoa.
Thank you. Any other questions?
Probably a bit of a dumb question, really, but is the
I hope so.
through? Is climate change, is that going to have any effect on volcanic activity?
It has effects on everything. It will subtly. I don't think it's the biggest. It's not what I'd put on my top of my list in terms of worries about. But yeah, so if we look at like the last glaciation, the retreat of the ice after the last glaciation, we see the volcanoes in Iceland react. So you unload the ice off Iceland and actually slightly increase the magma flux because it's decompression melting there. So if you're unloading that as well, so you see a measurable but subtle reaction in Iceland. You see an even more muted reaction to deglaciation in subduction zone or arc scale volcanoes. Arc volcanoes, because that's not decompression melting, that's changing in composition that's going on there. The other thing that will happen is as ice caps on volcanoes melt, their flanks will become less stable. So we'll probably have some flank collapses going on. So there definitely will be reactions. I mean, another positive thing, maybe if we're trying to find positives in climate change, if you get rid of all the ice on volcanoes like Galeras, then you're less likely to have lahars eventually, because actually one of the most tragic volcanic events of recent times was when tens of thousands of people were killed by the melting of the ice cap on Galeras, and then these enormous lahars, Nevada de Ruiz, these enormous lahars went down the side of the volcano. So you could look at that positive, but yes, I mean it's change, so change will change the hazard, but it's not, it's not an alarmist thing. It's not going to make a sort of step difference in the hazards from volcanoes.
One more question.
Yes, I was just wondering, this is all about the crust, isn't it? The Earth's crust. Is there any way of studying what's inside? I mean, is it just a great big mass of magma? Or?
So the magmas are sourced from the mantle. So we have the crust on the top and then the mantle underneath. So yeah, we do get insights into the mantle geochemistry from lavas coming up in different places. So some of my colleagues, I'm a volcanologist, and I'm interested in volcanic activity, but I actually, have colleagues for whom the volcanoes are really just vessels. They bring up the clues from the deeper earth for them to study. So sometimes it's just in the chemistry of the kind of, I don't want to call them boring rocks, but they're normal. But sometimes you get these really, like if you go to Tenerife, for example, you see these amazing green clots of crystals in the Tenerife lavas, and those are deep. We call them xenoliths, so foreign rocks, and those are bits of kind of deeper gubbins, possibly from the mantle that has been brought out, which are very olivine rich, which is the green mineral. So some of my colleagues, the volcanoes are just the conduits to get those juicy bits of deep stuff up for them to study. They're very limited human beings, but I don't
I'm now going to ask Barry Wright to give a vote of thanks, and then continue on afterwards with a
Well, I'll keep it brief, but thank you for a really wonderful talk this evening. I mean, I think it's obvious we hold you in high regard because we had you here a couple of years ago and we asked you back.
I begged.
Hold you in high and you were working on a different timescale from the volcanoes because it's 200,000 years.
As a scaling factor.
In fact, and you clearly don't tramp around, you clearly walk with purpose around our world and looking at various volcanoes. And I think most of us, really understood volcanoes in terms of paper mache and non-sonography and aerial imagery and all the other things like laser beam digital technology that you've talked about, which is wonderful to hear about. And who knew that volcanoes gave us upstairs toilets? I mean,
They destroyed the first upstairs toilet.
I think, medics really do destroy themselves and rebuild themselves and destroy themselves, and hopefully rebuild themselves again at the end. And it was wonderful also to hear you reading from your book, and we're very proud to be the first people who have heard an excerpt.
It's Tempest House.
I hope you'll give us an acknowledgement. But there is a strong bond, I think, between Tempest Anderson as one of our founders, gave us this building, worked in this building, lived in this building, and yourself and the things that you do. So hopefully we will see you again at some point in the future. So thank you very much for